Hi, 7.2 linear discriminant analysis. So first idea. So suppose that there are G classes and the predictor is the p-dimensional and the p is larger than or equal to G minus 1. And then there are the two steps in the linear LDA. So at first, project the p-dimensional predictor space onto the most efficient G minus 1 dimensional vector space to separate the G classes by linear transformation and write the map as x to y. So suppose we have 20 variables, but the two categorize those observations into, for example, the 5 groups. Maybe some variables are not useful. So we have to use maybe just the first variable and maybe 5th variable and the 12th variable. So we have to choose the variable, and also we allow the linear combination. For example, the average of the first 3 variables may be very good predictor for the category. So we summarize the information of the p-dimensional vector. Typically, that it has the very high dimensional vector into the low dimensional vector. So this is especially useful, for example, for the image processing. So image is very high dimensional data. 1000 by 1000 pixel data is the 1 million dimensional. So that we compress the data, then we can do the job efficiently. So at first, we project the data into a smaller space. Then the second step. The second step is to fit the J-1 dimensional density for Y in the J's group. And we assume the variance of those FJs, F1 to FG. So those are diagonal and the variance are the same for all J's. And this rule that makes all boundary linear in the space of X and also in the space of Y. So that's why that we say this as linear discriminant analysis. So X to Y is linear transformation. So if it's linear in Y, then also linear in X. So illustration. So originally the observations are in a high dimensional space. So high dimensional space that we cannot write on the the iPad, but okay, so we have the high dimensional space, the x1, x2, x3, up to xp. And we have the high dimensional space, so we cannot really imagine the groups, but the first group and the second group and third group, maybe triangle. But if we see this from the specific angle, that we can actually divide these groups very well. So that is often the situation. For example, the character recognition problem. So if we have 3 groups, that we only have the 2-dimensional space. We need only 2-dimensional space in LDA. So if we choose some transformation very efficiently, then transformation that looks like this. So that we have transformed the variable, I would say maybe y1 and y2. Then groups may be categorized as this way, so almost entirely distinguishable. Maybe the some but observation like this. But in this case, we can see how to divide the observations. For example, in this case, probably like this and like this and like this. Then we can separate the 3 groups. So this part is the step 1. So first one is this part is step 1, and the step 2 is making this linear discriminant. So that is actually based on the normal density, such as this. So this is the normal density, and this is normal density for the triangle class, and this is the normal density for the crosses. Then we can calculate the likelihood for each given observation. For example, each given observation, that we can calculate the probability that this point is belongs to this the blue class or this the black class and or red class. So then we can calculate the probability. So this is the step 2. And because of the restriction that we fit this contour of the multivariate, the normal density, all boundaries are linear. So all boundaries are linear. So if we have that restriction, actually we only have the 2-dimensional space to separate the 3 groups. If we have the 4-dimensional space, still it's possible, but it's actually redundant. Yeah, so if we think about just we only have the case that we only have 2 groups, then it's clear that we only have the one axis, right? So because we have 2 groups, and suppose we have the 2-dimensional space, then is it better than 1-dimensional space? Actually, no, because for example, if we have the one class as this and the other class as this, it looks useful, but that means that we have the boundary here. So if we think about this direction, actually it's enough to summarize the information. So anyway, the boundary is linear. So that means for 2 groups, we only have 1 dimension. And the 3 groups, it's a little bit harder to imagine, but actually the 2 dimension is sufficient. So this is the idea of the linear discriminant analysis. And how to do this, how to find the most efficient projected space mathematically. So that is the next slide. So this is basically a similar idea to ANOVA. So we think about the within group covariance and also the between group covariance. So within group covariance is this. So remember that the X is originally p-dimensional vector. So this is the p-dimensional, and this is p-dimensional transposed. So actually this part is the P by P matrix. And we have basically the sum of squared residuals. But you can see this is the within group. So for G's group, the mean is the X bar G, and we subtract each observation in G's group minus the mean of G's group. So this is the observation. So the sum of squared within group. So if we have the second group, okay, so first group is here and the second group is here, then so this means that we have the center for the G's group, and we think about just the distance within group and take summation. So this is actually the P by P matrix. So it's more complicated for multi-dimensional case, but basically this is the within group. And for another group, maybe G bar, maybe X bar, the G something, maybe G prime, then we calculate the within variance. So within variance, it's smaller is better. So if in a projected space, if variance is small, then separation is good. And the between group variance is, so larger between group variance is better. So between variance means that we have the overall mean, then this group and this group are well separated. So that means the distance between X bar and the group mean, X bar G or X bar G prime, is large, then it's better. And that is defined by this. So xg bar minus x bar and xg bar minus x bar. So this is again the P by P matrix. So compared to W, if B is large, then it's good. And it's a little bit hard to quantify this, but basically if we choose the p-dimensional vector A such that this quantity is maximized, then that is the most efficient coefficient to transform from X to Y. So A transposed X is the most efficient variable to distinguish those groups. Yeah, but this only makes the one coefficient, so one linear transformation from x to y. So if the g is more than 2, then we choose the g minus 1 vectors. We have to choose the g minus 1 vectors of A. And actually, this A is obtained as the eigenvector for the largest eigenvalue. So all eigenvalues are positive here, and the largest eigenvalues of this matrix, the W inverse B, the largest eigenvalue of eigenvector of the W inverse B. So that gives the best coefficient for linear transformation. So for if G is larger than 2, then we choose the G minus 1 eigenvectors for the G minus 1 largest eigenvalues. So x2, this vector. So this is the best transformation. So typically X is high dimensional, such as 100 dimensional. But here, if we have 3 groups, only 2 dimensional. Yeah, so in the next video that we explain an example, I explain the example for this linear discriminant analysis.